Hello and welcome to this talk on forward and backward private conjunctive searchable symmetric encryption. This is joint work with Devdeep Mukhopadhyay. With the advent of cloud computing, more and more individuals and organizations are generating extremely large databases in a variety of formats. Naturally, these databases cannot be stored or processed locally and must be outsourced. Note that even after the client outsources its database to a third-party cloud service provider, it still wishes to execute queries on the data and retrieve back the results. This task would be extremely simple if the data could be stored in the clear and the service provider was trusted. Unfortunately, this is not the case in the real world, and as a result, the client might wish to use some kind of cryptographic techniques to encrypt the data before offloading its storage to the cloud service provider. This gives us a big challenge, namely, how do we compute directly on the encrypted data without decrypting it? An ideal solution in this regard would be one that would process the query extremely efficiently while leaking very little information to the server. Unfortunately, existing solutions can be broadly classified into two categories. The first one consists of extremely elegant crypto techniques like fully homomorphic encryption that leak very little information to the server but are not yet efficient enough to be deployed at scale. At the other end of the spectrum, we have extremely efficient solutions such as deterministic or property-preserving encryption, and in fact, these are being deployed in practice by startups and organizations. However, they leak a lot of information to the server, and in many cases can be broken by attacks such as leakage abuse attacks. In this work, we focus on searchable symmetric encryption, a solution that attempts to achieve a good trade-off between security and efficiency, and so lies somewhere between these classes. In this paper, we propose a new SSE scheme called Oblivious Dynamic Cross-Tags, which is the first practically efficient dynamic scheme that supports searching over arbitrarily structured encrypted databases, allows fast and single-round searches for conjunctions of keywords, allows fast and non-interactive updates, and most importantly, achieves both forward and backward privacy, which are the de facto security notions for any dynamic SSE scheme today. We place our contributions in context with the existing literature on SSE. Note that this list is non-exhaustive, and I apologize in advance if I missed out on some of your favorite existing SSE constructions. The main takeaway here is that for very simple query types, such as single keyword searches, there exist dynamic SSE schemes that are both forward and backward private. Unfortunately, this is not the case for richer query types such as conjunctive and disjunctive SSE schemes. And so we make the first progress in this direction. Here is a little bit of background on dynamic SSE. Typically, we use a database representation where the database is a collection of documents. Each document is associated with an ID and is tagged with a set of keywords. And we build an inverted search index on top of the document collection in order to facilitate efficient searches. In the setup phase, the client generates an encrypted database and an encrypted search index and offloads these to the server for storage. Thus, in the search algorithm, the client typically generates a search token and sends it to the server. The server uses this token to process the encrypted search index and the encrypted database and returns the corresponding result. For example, suppose that the client wants to query for all documents containing the keyword Alice, then it generates a token that somehow encapsulates this information Alice and allows the server to come back with the set of encrypted documents containing the same. Similarly, during update, the client generates a token called an update token and sends it to the server, which the server uses to process the encrypted search index and the database and then returns either success or failure. For example, suppose that the client wishes to add document 6, which contains Alice and Mac. Then it generates an add token, which somehow encapsulates this information and allows the server to perform the corresponding update operation, at the end of which the server returns success. Now we come to the security notions for dynamic SSE, namely forward and backward privacy. Forward privacy is a notion that has been around since 2005 and informally requires that previously executed search queries do not leak any information about future updates. Backward privacy is a much more recently introduced notion which requires that future search queries reveal no information about previously deleted documents. Why do we care about these notions? Because there exist works that show that a dynamic SSE scheme that does not achieve these two notions of security can be exploited or broken by leakage abuse and file injection attacks. Here's a somewhat more formal description of forward privacy following the definition introduced by Bost in CCS 16. Suppose an insert or delete operation involves a keyword and a document identifier, then the corresponding update token should computationally hide this keyword and document identifier information. In the example before, when the client wants to add document 6 containing Alice and Mac and sends the corresponding addition token along, this token should hide from the view of an honest but curious server the information 6, the keyword Alice, and the keyword Mac. Here's a somewhat formal description of backward privacy as introduced by Bost, Mino, and Orimenko in CCS 17. Suppose two consecutive search operations on a keyword happened at timestamps T1 and T2. And suppose that in the interim, a document with identifier ID which contained this keyword was inserted and then deleted. Then the search operation at timestamp T2 should reveal no information about this particular document. In other words, consider two scenarios. The first scenario where a document with identifier ID containing this keyword was inserted and then deleted. And scenario 2, where a document with identifier ID prime containing this keyword was inserted and later deleted. Then from the point of view of an honest but curious server, the search operation at time T2 should be computationally indistinguishable. A natural question to ask is the following. Since we already have forward and backward private dynamic SSE schemes for simple queries like single keyword search, can we not somehow trivially or naturally extend them to conjunctive keyword search? Well, it's not as simple. Consider a conjunctive query of the form, retrieve all documents containing Alice and Bob and crypto. A natural approach is to break this query up into 3 single keyword queries, and then use a forward and backward private SSE scheme supporting single keyword search to run these 3 queries in parallel. Later on, the client can locally compute the intersection of the results. However, this approach has certain disadvantages. The first is with respect to efficiency. Note that the only document that's relevant to this query is 1, yet we did a total of 8 or 7 retrievals. And this is obviously a waste of computational resources and communication resources. Secondly, we should ideally retrieve only document 1 and then check if it contains both Alice and crypto. This approach, unlike the previous approach, has computation and communication that is proportional to the frequency of the least frequent keyword. The next challenge is with respect to security. The naive approach leaks a lot of information that is additional to the final result. It leaks the documents 1, 3, and 5, in particular 3 and 5, which are not relevant to the final outcome. It really leaks that these documents contain Alice. It also leaks information such as document 5 contains Alice and crypto, but not Bob. Why is this bad? Because in previous works, it has been shown that such sub-query leakages can be exploited to break the query privacy of a conjunctive SSE scheme. And so we do not want solutions that lead to such leakages. Here is an overview of our approach for addressing this situation. We start with Mitra, an extremely efficient forward and backward private SSE scheme that only supports single keyword search and was proposed by Chamani et al. In CCS 18. We then perform this naive extension as described earlier to get a scheme which we call as Mitra conjunctive. As already described, this scheme has search overhead that scales with the frequency of the most frequent keyword in the conjunction, which is not desirable. It is also not backward private because it has a lot of leakages that can be potentially exploited. In the next step, we introduce our first technique, which we refer to as dynamic crosstalks, and we build a scheme called basic dynamic crosstalks. This is extremely efficient with respect to updates. It's also forward private, and it also achieves a search overhead that scales with the frequency of the least frequent conjunct as desired. However, it requires an additional round of communication during searches, and it's also only weakly backward private. We then augment this scheme further using our second technique called oblivious tag computation. And this gives us our desired solution, which is oblivious dynamic crosstalks. This has search overhead, again, that scales up with the frequency of the least frequent conjunct. It also has one round searches and achieves the desired backward privacy notions. Here is a very, very high level overview of our intermediate construction, basic dynamic crosstalks. We introduce a specially designed data structure that has 0, 1, or 2 entries for each document keyword pair. When a document keyword pair is added, a new entry encrypting this information is inserted into this data structure. Similarly, when a document keyword pair is deleted, another entry encrypting this particular information is inserted into the data structure. Note that these two insertions, from the point of view of the cloud service provider or the server, are computationally indistinguishable. We make an assumption here that the identifier for each new addition operation is freshly generated, but this is standard in the dynamic SSE literature. How does this data structure help us? We show that using a specially designed token, we can allow the server to check in big O of one time or constant time whether a particular keyword document pair was ever added, and if yes, whether it was subsequently deleted. And we do this in a manner that ensures that the server does not learn the document identifier or the keyword in the process. Given this additional data structure, now consider the conjunctive query as seen earlier. And here is a very simple two-round solution. In round one, perform a single keyword search for Bob, which is the least frequent of the three keywords, and retrieve document one. Now in the second round, use this particular data structure, generate the tokens that will allow the server to check in constant time if 1, Alice was inserted and not deleted, 1, crypto was inserted and not deleted. If the server sees that the response to both these queries is yes, then it asks the client to include document 1 in its final output set. Otherwise, it asks the client to discard it. Note that this is correct, and the computation is proportional only to the frequency of the least frequent keyword in the conjunction. The disadvantage is that it requires an additional round of communication, and this is what we address in technique 2, which is oblivious tag computation. Unfortunately, there are many details that I do not have the time to go into, and I request you to look at the paper for the same. Here is a summary of our final scheme. It conforms to the widely accepted structured encryption framework introduced by Chase and Kamara in AsiaCrypt 2010. It uses specially designed data structures for dynamic crosstalks that support efficient forward private updates, efficient backward private one-round conjunctive keyword searches, and can be implemented in practice very efficiently using dictionaries and Bloom filters. ODXT incurs very basic access pattern and volume leakages that actually satisfy existing backward privacy definitions. However, given an application that requires even lower leakages, ODXT can still be used because it is compatible with existing leakage suppression techniques. Finally, ODXT resists known leakage abuse and file injection attacks. This is verified experimentally. Here is a one-slide summary of a prototype evaluation. We compared ODXT in terms of its search performance and storage overheads with Mitra Conjunctive and two other schemes, IEX2LEF and IEX-ZMF, introduced by Kamara and Moataz in Eurocrypt 17. We show that in almost all of the cases, especially with respect to most frequently encountered keyword queries, conjunctive keyword queries, ODXT outperforms or matches closely all of these existing schemes. There are a few corner cases where the keywords in the conjunction have very low or very high frequency, where ODXT may be outperformed by Mitra Conjunctive. But in the paper, we have special boosting strategies that allows ODXT to be competitive even in these cases. I refer to the paper for more details. Finally, I would like to end with a series of open questions. The first one is whether one can extend ODXT to also support disjunctions and general Boolean formulae over keywords. Note that we can support formulae that are in a special conjunctive normal form. However, it is not efficient for arbitrary Boolean formulae. The next question is more foundational. What are the ideal backward privacy guarantees for conjunctive keyword queries? In particular, are the guarantees achieved by ODXT sufficient? The third and final question is whether more extensive leakage-based cryptanalysis could show some more vulnerabilities of ODXT, and we invite the crypto community and the security community to try out the same. Thank you very much for your attention, and I'm happy to answer any questions that you might have.